Hello everyone. In English, there is a saying, in the competitive world, in order to stay where you are, you have to keep running. So, what I want to say here is, keep learning. Welcome to the computer science class. That's data representation. In the last class, we have seen about the number systems. Just let us try to recall. In number systems, which are different types of number systems, we have seen. We are familiar with decimal number system. We have seen binary number system, octal number system, and hexadecimal number system. In decimal number system, we have seen that there are 10 symbols. So the base is 10. So how many symbols? There are 10 symbols in it, starting from 0 to 9. Similarly, binary number system. What is the base? Base is 2. Only 2 symbols we have, 0 and 1. Why the binary number system is important for us? Because computer can understand a language of 0 and 1. It can't understand, suppose you have written something in English, it has to be converted to the language of zeros and ones. Just like when, for example, when our Prime Minister comes to Mangalore or Bangalore, usually he will deliver his speech in English or Hindi, which will be converted to either Kannada or the local language by one more translator. Similarly, whenever we are going to write the program in English, of course we are writing the program in English, that will be converted to a language of zeros and ones by either the compiler or the interpreter. Those things we shall see later in the programming. But the base for everything is binary number system, and it has got two symbols which are 0 and 1. Similarly, octal number system we have seen. What is the base here? Base is 8. That means what? There are 8 symbols in it. Then comes hexadecimal number system, where the base is 16. 0 to 9. Then comes A, B, C, D, E and F. And one more thing we have seen in the last class. For example, suppose you write a number. Suppose I write 102. Whether it's decimal, binary, octal or hexa. Of course 2 is there, that's why it can't be binary. But still, there are 3 more number systems. That's why we have to mention the base for it. Suppose the base is not given, then it is decimal. But for decimal also we can write the base like 10. Or suppose it's written as 8, then it is octal number. Remember, we have emphasized, that means we have given the stress on the numbers that, for example, suppose we have written 10 in binary number system, and also we have written 10 in octal number system. This is not equal to this, right? Also, which is not equal to 10 in decimal number system. Every number system is having its own base and its own value. That's why today we shall look into a concept called as conversions. So we shall see into conversions. If we write a number 156 in decimal number system, this is, see here its units, tens, hundreds. 10 to the power 0, 10 to the power, its weight is 10 to the power 0, 10 to the power 1, 10 to the power 2, right? So the weight of this digit is 100, that is 10 to the power 2. the digit which is having the highest weight, that is this one. That's why this is called as most significant digit, that is MSD. In short, it will be written as MSD. So similarly, this one is called as least significant digit, least significant digit, because it's in unit space. So it's also called as LSD. What's meant by MSD? Most significant digit, highest power, and 6 is LSD, that is least significant digit. Suppose we have a number like this, 256.89. What do we have here? Here we have a decimal point. It's called as decimal point. We are familiar with the decimal point. Now how it is different? Which is 10 to the power 0. This is integer part and this is the fractional part. So this will be 10 to the power 0 unit space, not this one. That is 6. Before the decimal point, 10 to the power 0, 10 to the power 1, 10 to the power 2. Hope it's understood. Then what about this? This will be 10 to the power minus 1. This will be 10 to the power minus 2. What does it mean? See here, when we write this 8 and just compare that with 6. When we write this 6 will be written like this, 6 into 10 to the power 0. Or we shall write this one, 2 into 10 to the power 2 plus 5 into 10 to the power 1 plus 6 into 10 to the power 0. It holds good for all the number systems. Here it is decimal, that's why we have written it as 10. If it is octal, it becomes 8. If it is binary, it becomes 2. If it is hexa, it becomes 16. Now after the decimal point, what we should do? Plus 8 into 10 to the power minus 1. See here, this is 6 into 1, 10 to the power 0 is 1. This is 5 into 10 to the power 1 is 10, that is 5 into 10. This is 2 into 10 to the power 2, that is 2 into 100, that's why it's 200. Now when we come to this 8, listen carefully. We will write it as 8 into 10 to the power minus 1. What does it mean? This could be written as, I will write it here just for your understanding. This could be written as 8 into 1 by 10. That is 10 to the power 1. 1 by 10 to the power 1, which is nothing but 10 itself. So when you get this 10 from the denominator to the numerator, it becomes 10 to the power 1. The meaning of that is 8 into 1 by 10. Similarly, when you write this 9, how we can write this? Plus 9 into 10 to the power minus 2. That is what? That is equal to 9 into 1 by 10 to the power 2, which is nothing but 1 by 100. When you multiply this 1 by 100 into 9, you will get its positional value. All those things we shall see when we are going for the conversions. Okay, this is with respect to when we talk about decimal number system, octal number system and hexadecimal number system, we call it as MSD and LSD. After looking into which is having the highest weight or highest value, positional value, and which is having the least positional value. So comparing the same with this particular number, which is MSD here Of course, that is 2. Because 2 into 10 to the power 2. Which is having the least value? Is this one or this one? Least value in this is this position. That's 10 to the power minus 2. So here MSD is this one and LSD is this one, not the 6. Suppose the fractional part is not there, then it is 6. In this case, it's 9. Hope it's understood. Now, coming to the binary number system. When we talk about the binary number system, we don't call it as digit, we call it as a bit, because 0 and 1. So instead of digit, we write it as bit. So instead of MSD, we call it as MSB, most significant bit and least significant bit. So if we want to take an example, we are going to talk about the same thing many times. So if there are any confusions after practicing 2 or 3 times, those doubts will get cleared. See, 1 0 1 1 base 2. What is this? This is called as MSB, most significant bit. What about this? This is called as LSB, or least significant bit. If we have 1101.101 to the base 2, what about this? This is a binary number because base is 2, which is MSB. This is MSB because 2 to the power 0. Remember, this is, don't call it as a binary point, decimal point. Here it is binary point. This is called as binary point. Binary point. In decimal number system, it's called as decimal point. Here it's called as binary point. Positional value is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. This is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3. Right? That's why this is MSB. Which is LSB here? This one, not this one. This is LSB. And this is MSB. Now we shall look into the conversions. What meant by conversion here? A number in one of the number system will be given. For example, 23 to the base 10 is how much in base 2? I would like to repeat. 23 base 10 is how much in base 2? Already we have seen, suppose we have written 10 in decimal number system, it's not equal to 10 in binary number system, because binary number system has got only 2 bits or 2 symbols in it. In the last class also we have discussed, see, when we write the binary number system starts from 0, then 1, no other symbols. So next symbol is 1 0, next one will be 1 1. Usually we will have a standard in the sense, whenever a value is represented with respect to how many bits you are going to represent it. If we want to represent the bits with respect to 2 bits, even if you write 0, with respect to 2 bits we shall write. So if you add a 0 to the left side, the value doesn't change, right? If you add a 0 to the right side, always the value changes. 1 becomes 10, right, in decimal number system. Then 10 becomes 100, the value changes if you add a 0 to the right side. But if you add a 0 to the left side, prefix, the value doesn't change. That's why if you want to represent the number with respect to 4 bits, 0 could be written as 0 0, 1 can be written as 0, 1 because we are maintaining a standard. After this, again with respect to 2 bits, it's not possible to represent any value. We have to go for one more bit. Just like after 9 in decimal number system, we will write 10. After 99, we don't have any other symbol with which we can represent with respect to 2 symbols. We have to go for 100 in decimal number system, that's 100. Similarly here, after writing 11, with respect to 2 bits, we don't have any other symbol, so we will take one extra bit, 100. Then 101, 110, 111. Now, suppose we are asked to write the numbers with respect to 3 bits. Up to here only 2 bits. Up to here, then from here to here it's with respect to 3 bits. What we need to do? Add a 0 to the left side. If it is asked to represent the binary numbers with respect to 3 bits, right? Now see, this is binary. When we write the decimal, if it is a decimal, it will be 0, 1, 2, 3, 4, 5, 6 and 7. 7 in decimal is equal to 111 in binary. Just a repetition of the last class. But some of you may be having some doubts in it, that's why I am repeating. Once we have reached 7, now the question is it possible to represent 8 with respect to 3 bits? No, it's not possible, because all other possibilities, 111 is the highest one, just like 99 in decimal. We can't have any other symbol with respect to two symbols. We can't represent any other number. So here also, with respect to 3 bits, we can't have any value which is greater than this. That's why we have to go for one extra bit, that is 1000. 1000. I write it here, 1000. Then 9, 1001, 10, 1010, 11, 1011, 12, 1100, 13, 1101, 14, 1110 and 15, 1111. See, once we have reached 15, with respect to 4 bits, all possibilities we have written. That's why whenever we are going from 0 to 15, with respect to 4 bits, it's possible to represent. But beyond 15, one more extra bit we have to add. So if it is asked to represent the number, decimal numbers, with respect to 4 bits, then you have to add a 0 to the left side. Up to 7, it's possible to write, see, 0 and 1, only 1 bit. But from 2 to 4, 0 and 1, only 1 bit. Up to 3, with respect to 2 bits we can represent. But from 4 to 7, we need to have 3 bits. Beyond 7, that is 8 to 15, we have to take 4 bits. This is how the numbers will be written in binary number system. We will get confused here. See, it's easy. Up to 3, we can write 00, 01, 10, 11, right? The combinations. 00, 01, 1. Forget about other things. 00, 01, 10, 11. Okay, then just have a look here. I will just mark here. Mark here. What is this? 00, 01, 10, 11. Same thing get repeated. Then from 8 to 11, 00, 01, 10, 11. The same thing will get repeated. Then 00, 01, 10, 11. Again, same thing will get repeated. Then see here. 0, 1, 0, 1. That means it toggles. Toggles in the sense changes its state. 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. alternate positions. Then the next one is 0 here. Once you have written 0, here it changes every time. It retains its position for 2 places, 0, 0. Then it becomes 1, 1 and 1. Then again changes 2 times, again 2 times, then 2 times. Here also 2 times, 2 times, 2 times, twice. Right? Then just have a look here. 0, 0, 0, 0. How many times? 4 times. Then it changes. 1, 2, 3, 4. 4 times. Then again it changes 4 times. 4 times. These are the different ways how we can remember that. Then what about this? 1, 2, 3, 4, 5, 6, 7, 8. Again 1, 2, 3, 4, 5, 6, 7, 8. Just to confirm whether you have written it properly or not. So alternative, twice, 4 times, 8 times. Now once you know this, after this, that is 16 to some 32, you can write easily. Okay. And just for your information, now we shall come to the original problem. 23 to the base 10 is how much to the base 2? What we need to do here, whenever we are converting from decimal to any other number system, divide with respect to the base to which particular number system we want to convert. So in this number system 23, divide with respect to the base to which we want to convert. So to which particular base we want to convert, that is to binary. Right? So here we can write this is decimal to binary. Decimal to binary. Look at the base here. So we are going to convert it to the binary. Divide this number with respect to 2. We will get the quotient and remainder. Don't write something point something. No. You have to write separately the remainder and the quotient. First write the quotient, then write the remainder. That is Bhagalabda Matte Sesha. First you write the quotient. 23, how many times? 2 11s are 22. Yaradan only 22, right? So 2 into 11 is 22. Right? What we have here is 23. So 23 minus 22 is 1. So write that. So what is this? This is quotient and this is the remainder. Write in the format of the quotient and remainder. Bhagalabda Matestesha. Keep on dividing the remainder. Once we have written this one, now don't touch this, just keep it as it is. Now divide this 11 by 2. How many times? 2 into 5s are 10. Right? What we have is 11 here. 11 minus 10 is 1. So how many times? 2 into 5s are 10. How much is remaining? 1 is remaining. Remainder is 1. 2 5 10. 10 minus 11 minus 10 is equal andre 1. Right? Quotient and the remainder. Keep on dividing the quotient. Once you have written this one, don't divide this one once again. Don't divide this one. Only we have to divide with respect to the quotient. So 2. 2 2s are 4. So twice. And 5 minus 4 is 1. Then again divide. How many times? 2 1s are 2. Right? 2 1s are 2. Whether there is a remainder, Seshonta illa. So 0. Either we can stop here or we shall do one thing. Keep on dividing the remainder till the quotient becomes, keep on dividing the quotient till the quotient becomes 0. I repeat, keep on dividing the quotient till the quotient becomes 0. Once we divide 1 by 2, is it possible to divide? Don't write it as 0.5. We can't write. Integer part we have to write. Can we divide? No, it's not possible. Then what is the remainder? 1. ಒಂದನ್ನು ಎರಡನ್ನು ಡಿವೈಡ್ ಮಾಡಲಿಕ್ಕೆ ಆಗೋದಿಲ್ಲ. ಹಾಗಿರುವಾಗ ಶೇಷ ಎಷ್ಟಾಯಿತು, ಅದನ್ನು ಶೇಷದಲ್ಲಿ ಬರೆದರಾಯಿತು. ಸೊ ದಿಸ್ ಬಿಕಮ್ಸ್ 0. Now once again we will repeat. The number is given. What we want to do, we want to convert this one decimal number system 23 to binary number system. So take the number, divide by the base, that's 2. So divide and write the remainder and the quotient. First you write the quotient, then you write the remainder. Then once again divide the quotient, don't touch the remainder after that, and write the quotient and remainder once again. Keep on doing the same till the quotient becomes 0, because once the quotient is 1, when you try to divide that, the quotient will be 0 and the remainder will be 1. Hope here there is no confusion, because we can't write 0.5. Integer part we have to write. 1 we can't divide by 2, because the 1 becomes remainder itself. Once it's done, now we have to look into this part. Which part? The remainder part. Start writing the remainder from the bottom to top. What is the last one? That's 1, then comes 0, then comes 1, then comes 1, then write 1 to the base 2. Bottom up. This way we have to write, not this way. This way we have to write. So what we can say here is 23 to the base 10 is equal to 10111. There is a technique to check whether we have written it properly or not. How it is? See, what could be done here is, when we write the binary number systems, we write the positional values or positional weights. How is that? That will be 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, etc. 2 to the power 0 is how much? It's 1. 2 to the power 2 is 2. 2 to the power 3 is 2 into 2 into 2, that's 8. 2 to the power 2 is 2 into 2, that's 4. 2 to the power 3 is 8. 2 to the power 4 is 8 into 2, that is 16. Like that it continues, because 2 to the power 5 will be double of this one, that will be 32. So 2 to the power 1, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, and 2 to the power 5 is 32. Now, when we have this number 1, 0, this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. This is just to check whether the value that you got is correct or not, just to cross verify it. It's not compulsory to do it. What we will write here is 2 to the power 4, 0, 1, 2, 3, 4. So we don't want this one. And just write the values here, 1, 0, 1, 1 and 1. Just add up these values. Add up these values here, for which there is a 1. If there is 0, just leave that. So what's the value here? It is 16. Next one is 8, so just leave it. Then write 4, then 2, then 1 you write. 16 plus 4 is 20, or 6 plus 4 is 10, 11, 12 and 13. 1 in hand, it becomes 23. So whatever we have done is right, isn't it? Suppose we had, see, this is right, what we have done is right. Suppose we had a value something like this, 1, 0, 1, 0. In that case, what to do? That will be 1, 0, 1, 0. I leave this one. Anyhow, this position is not there. This position is not there. So what to do in that case? What will be its value? 2 to the power 3, that is 8. This one has to be written 8. 2 to the power 2, 0, right? Just leave that. 2 to the power 1 is 2. So this will be 10. Just to verify it. Of course, this value we didn't get. I want to just tell you what we have to do where the value is 1, what we should do where the value is 0. 0 ಇರುವಲ್ಲಿ ಅದನ್ನು ಆ್ಯಡ್ ಮಾಡಲಿಕ್ಕಿಲ್ಲ. ಇಲ್ಲಿ 1 ಉಂಟ ಆ ವ್ಯಾಲ್ಯೂಯನ್ನು ಆ್ಯಡ್ ಮಾಡಿ. ಇದನ್ನು ಫಸ್ಟ್ಗೆ ಸೈಡಲ್ಲಿ ಬರ್ಕೊಳ್ಳಿ. ಇದು ಕ್ರಾಸ್ ವೆರಿಫೈ ಮಾಡಲಿಕ್ಕೆ ಮಾತ್ರ. $53 or some other number you write 71. 71 to the base 10 is how much to the base 2? What we should do? Write the 71, divide by 2. 35 plus 35 is 70, right? That means 35. 71 minus 70 is 1. Again divide. 17 plus 17 is 34. So 17 and 1. Divide by 2 once again. 8 and 8 are 16. Again divide by 2. 4 plus 4, 2 4s are 8. Is there any remainder? No. So in these cases we had, see, 71 minus 70 is 1. 34 minus 35 is 1. Of course here we have, it is 8. So 2 4s are 8. 4 times. 8 minus 8 is 0. Again 2. It's 2, 0, 2, 1, 0. Divide by 2, it is 0, 1. Now let us see what we have to write. Bottom up, right? Bottom up. This is 1, 0, 1, 0, 0, 0, 1, 1, 1. I hope whatever I have written down is not visible. Just keep on dividing it, or I will write here once again. See, after writing 8, divide 8 by 2, it is 4 and 0. Again divide by 2, it is 2 and 0. Again divided by 2, it is 1 and 0. Again divided by 2, it is 0 and 1. Start writing from here, then write the values written this side. So it becomes 1, 0, 0, 0. Then this one, 1, 1 and 1 to the base 2. Now just to cross verify this is 2 to the power 0, that is 1, 2, 4, 8, 16, 32, 64. So which are the values that we need to add? 64 plus 4 plus 2 plus 1, 64, 68, 69, 70, 71. So whatever we have written here is 71, right? So this is 71. That's right. What we have done is right. Of course, a decimal number can have the fractions also. That conversion we shall see in the next class. Thank you.